Do you sometimes wonder how computers work? How does your phone understand data and then how does it respond to it? Today I will teach you how the number system works, how to use it, and where it's used. Hopefully you get something out of this video, and if you still don't understand, don't be afraid to ask in the comments. I love answering questions. Firstly, I'd like to begin with definitions. So if you do feel yourself not understanding certain words or terms, you can refer to this. Bits and bytes. Bits are the smallest digital unit and can either be 1 or 0 in binary. 8 bits make up a byte. LSB is the lowest value in binary. It starts on the right side, and MSB is the highest value, making it the leftmost. Digital positioning is like reading a book, except it's right to left. But then actually when you dictate or read the binary number, you're reading it left to right. Base is the size of a step you can make for every single digit. Also, base is determined by the amount of numbers inside of a numerical system. This will make sense in a couple of minutes. String is a continuous line of symbols. Power of the base, or exponents. The base is raised to a specific exponent given by its digital position. Grouping is organizing bits into a set of specific sizes. An example would be hexadecimal. One symbol is 4 bits. In octal, one symbol is 3 bits. Binary coded decimal is binary encodings of decimal numbers where each digit is represented by a fixed number of bits, usually 4 or 8. Not to be confused with grouping. BCD is specific for binary to decimal, hence in the name, while grouping is a broader term which is used for other numbering systems. Finally, I can begin with the numbering systems. Let's begin with binary. Now, how does binary work? The ones and zeros have meaning.
Yeah, no shit, Sherlock!
And it can be translated into numbers humans can understand with math, but there's a quicker and more popular method, which is just doubling the next number, which is why it's called base 2. How it works is binary goes by digital positioning system, right to left. So the first bit on the right starts with 1, and the next gets doubled, and the next gets doubled, and so on. As you can see in this binary string 10000100, 64 and 4 have 1s. This means that these two numbers will get added together, giving you 68. Binary doesn't only need to be converted to a value. It has multiple uses, such as in electronics or logic gates. It can either be an on or off state. For an example, if you are using an AND gate, it will require both states to be high for the output to be high, else the output will be low. And binary can be also used for ASCII, or letters basically. It gets a little more complicated in that because ASCII is an encoding system, and that allows you to kind of transfer binary into letters. So you can kind of make meaning out of zeros and ones. Now that you hopefully understand, let's get on with the second number system. It is the one you should be familiar with. If not, I wouldn't be surprised if you were a vegetable. It's called the decimal system. It's used everywhere in life for money, measurements, and anywhere you see numbers. The decimal system is for humans to understand the value of something. Like when I converted 1000,100 to 68. 68 was the decimal value. In coding, it is also known as base 10. The reason it's called base 10 is because it uses 10 unique numbers. Not so unique to a regular person, but for us, they're very unique. Representing symbols are 0 through 9. Moving on to a system you might have heard of and possibly seen already. When selecting a color, you might have noticed letters and numbers. Well, you can thank the hexadecimal system, a compacted binary system. It's used in computers, colors, byte addresses, and anywhere where there's a lot of data that you want to compact. Representing symbols are 1 through 9, A through F, and their decimal values are as follows. And since there are 16 symbols, it will be a base 16. In a base equation, 2f32 would be 2 times 16 to the power of 3, f, or 15, times 16 to the power of 2, plus 3 times 16 to the power of 1, plus 2 times 16 to the power of 0. And any positive value that is raised to the power of 0 will be 1, so it's 2 times 1. This will equal 12,082 as your decimal value. Another thing you should know is the size of a hexadecimal. Each symbol is worth 4 bits in binary, so 2f32 would be 16 bits, or 2 bytes. Converting a hex number to binary is straightforward. To do this, simply replace each hex digit with its 4-bit binary equivalent. For an example, 2f32 in binary is 2 equals 0, 0, 1, 0, f or 15 is 1, 1, 1, 1, 3 equals 0, 0, 1, 1, and 2 is 0, 0, 1, 0. This gives us the final binary representation. 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0. Now you see why it's better to use hexadecimal rather than sending out long binary strings. And the last system, Octal, or base 8, uses 8 symbols, 0 through 7. While it's not as common today, it was widely used in older Unix-based systems and legacy computers. You might still encounter it in some Linux or Mac permission-based environments, as Unix is their base for their operating system. Even though it's uncommon, I think it's still important to teach this because just in case you run into it. So octal 173 in a base equation is 1 times 8 to the power of 2 plus 7 times 8 to the power of 1 plus 3 times 8 to the power of 0, which gives you 123 in decimal. And unlike hexadecimal, octal groups into 3 bits and binary per symbol. So octal 173 in binary is 001111011. At last, I am finished animating this video, so I hope you learned something because I'm going to sleep.